So we will continue solving the question papers for the module 1, and then we'll go for the module 2 and module 3. So we are ahead of all the others. We have finished 3 units, 3 modules rather. That's why I thought it's better to check the question papers, and if there are any doubts there, we can try to clear it. So we have this question 2b, wherein it says you have the ST as the AM signal over here, and that is passed through a squarer. So that means you'll get AC squared 1 plus KAMT whole square cos square of 2 pi FCT. Now this cos square of 2 pi FCT can always be written as 1 plus cos 4 pi FCT divided by 2. So that will have 2 components. One is that 1 by 2, and another is cos of 4 pi FCT divided by 2. Now, if you pass that signal through the low pass filter, then that cos of 4 pi FCT term will be filtered off, and it will pass only AC square plus 1 plus KAMT whole squared divided by 2, because we have half there in place of the term over here. If you square this term and simplify, you'll get half plus cos of 4 pi FCT divided by 2. The cos of 4 pi FCT divided by 2 will go off because of low pass filter, and what is left is 1 by 2. So whatever we have here, this term squared divided by 2 is what will be V2T. And if you take the square root of that, then you'll get again only this term divided by root 2. You'll get, cos will not come, only this term will come, divided by root 2 is what we will get. So except for all the other things, right? Now if you try to expand that, then that will give you AC by root 2 plus Ka AC by root 2 into MT. Now if you just forget about the DC value AC by root 2, what is left is AC by root 2 multiplied by Ka into MT, where MT is the message signal. So message signal multiplied by some constant, and that constant is AC Ka by root 2 is what is important, which is shifted by AC by root 2, because that is DC value. Whenever you add a DC value, the AC signal gets shifted. Whenever you add a DC value, the AC value gets shifted. Please remember that above or below, depending upon the DC value is positive or negative. Positive or negative, the waveform will get shifted. So what we are left with is only the value of MT. We can get the value of MT. That's what you need to write. However, it's only 4 marks. So square, then expand this cos squared 2 pi FCT into 1 plus 4 pi FCT divided by 2. Then after passing, you will get AC square plus AC squared into 1 plus KAMT whole squared divided by 2. And after taking the square root r, you will get AC 1 plus KAMT divided by whole divided by root 2. And in this, the main component is MT itself. That's all you need to write. Okay. So then you have the C part, which is what is the vestigial sideband modulation. Explain the generation of VSB modulated signal and list the advantages. I think it's already done in the class. We've already done that, right? Vestigial sideband generation is what is asked. So here we have need generation is this figure, and you need to explain that. Then advantages you need to list. Okay, so demodulation is not needed. Generation just means modulation only. Okay, and the advantages are mentioned over here, and that's what you need to list. Okay, so let us go to the next paper. We'll first finish the module 1. Explain the generation of DSB-SC waves using wing modulator. This we have already explained in the earlier question paper also. We will not go through it again, right? Explain briefly on the following frequency discrimination method, phase discrimination method for SSB generation. Okay, so these two methods we need to discuss for SSB generation, right? Frequency discrimination method and phase discrimination method for SSB generation. So let us see where it is. Ring oscillator, coherent detection. This is Costas receiver. This is okay. Phase discriminator is there here in the Costas receiver for DSB-SC. We want for SSB-SC. SSB-SC is here. SSB modulation. Okay, frequency discrimination scheme for generation of SSB modulated wave is being mentioned over here, right? Then similarly, the phase discrimination method for SSB, is it there? No, phase discrimination method doesn't seem to be there. Okay, we'll find out that and tell you. Here, what is given is the frequency discrimination scheme for generation of SSB wave. Just check up if it is there. Please inform me on the chat box. Okay. Okay. So let us go to the next question. A broadcast transmitter radiates 20 kilowatts when the modulation percentage is 75. How much of this is carrier power? And also calculate the power of each sideband. So this is a general modulation. So the general AM modulation. So you need to write, the total power radiated is 20. 20 is equal to, this is PT is what is given. PT is equal to PC multiplied by 1 plus mu squared by 2. PT is equal to PC into 1 plus mu squared by 2. Mu is equal to 0.75 because this is 75%, right? So PC will be naturally 20 divided by, in the bracket 1 plus 0.75 squared by 2. So 0.75 squared, you need to expand that and try to write it, and that will give you the value. So that will be the value of PC. Then for each of the sideband, power in each of the sideband will be mu squared by 4. Mu squared by 4 into PC, right? Mu squared by 2 into PC will be the value of both the sidebands together. Mu squared by 4 into PC will be each of the sideband, okay? Each of the sideband. So PC is equal to 20 divided by 1 plus 0.75 whole squared by 2. And the value of the, what you call, each of the PLSB and PUSB will be equal to mu squared, that is 0.75 squared divided by 4 multiplied by the value of PC, whatever is calculated above. Okay, then you have the working of the envelope detector. Envelope detector we have already studied, right? We already studied the envelope detector. Same thing we just need to explain, right? So where is the envelope detector? Envelope detector will involve the demodulation. Whenever we talk about the what you call detector, it just means demodulation. Switching modulator. It's not modulator we want, it is detector. Okay, envelope detector is here, right? So envelope detector is this figure which is used for demodulation. You need to write all these and explain the write the explanation. Okay. Next we go for write a note on quadrature carrier multiplexing. Quadrature carrier multiplexing also we have already covered. Yes, quadrature carrier multiplexing, or what is known as sometimes quadrature amplitude modulation. QAM both are same. QAM and the QCM both are same. Then explain how Costas receiver can be used for demodulating the DSBSC signal. Again, this we have already studied. It was there in the earlier question paper also. So that can be solved very easily. Next, we go for the next question paper. Illustrate the time domain and frequency domain characteristic of standard amplitude modulation produced by a single tone. For single tone, we need to write that, right? Please try to differentiate that. When for single tone, the figure will be different. For multi tone, or rather a general empty signal, it will be different. So single tone will be the figure which corresponds to. So this is for multi-tone, single tone. This is multi-tone. Okay, this figure is for a general, empty, right? Then you have the single tone below. You should have below this. This is multi-tone. Why is going directly for multi-tone? In the slides, we might have used single tone, right? Single tone is MT will be equal to EAM cos of FMT. Did we not write that? This is for a general statement. For single tone, it will become here one lower sideband, here one upper sideband. That's all. So this will be the envelope detector for envelope waveform for single tone. Okay. I think you can try to write that. That's not a big issue for single tone. For the difference between single tone and multi-tone will be only that in multi-tone you have more number of modulating signals that will give you AM, FM1, FM2, and all that. So you will have so many of them. M1T is equal to AM1, AM2, and all that. But in single tone, you will have only a single term. I think this might not be there here. It might be there in the slides. Just check that up. There's nothing big about it. Only you need to write in place of this MT, you need to write the value of AM cos of 2 pi FMT, where KAAM will become mu. KAAM will become mu. So have we not written that? Is a question which I am asking myself. This is, yes, we have written this. This is single tone itself. I don't know why we have written this. Okay, this is single tone itself. But waveform cannot be that way, right? The value of EMT is written as AM cos of 2 pi FMT. This is what is single tone. When we write a single frequency and then you write this and then you write this and then you write this thing and you write a LSB with mu AC by 2 and MSB with mu AC by 2 and carrier with AC both on the negative and positive axis. That's not written in, figure is not written corresponding to that. But this is a more general term wherein we take the value of the MT in general. So, but otherwise for single tone, you need to write just a single, lower side band and single upper side band. Okay, you can do that. Then we have a carrier wave 4 sine 2 pi into 500 into 10 to the power of 3 t volts is amplitude modulated by the sine wave, which is something like this: 0.3 sine of 3 multiplied by 2 pi into 500 t plus 0.1 into sine of pi into 2 pi in 500 t volts. Determine the upper and lower side band and sketch the complete spectrum of the modulated wave. Estimate the total power in the side band. Estimate the total power in the side band. So might be the, somewhere the bracket has gone wrong. If I'm right over here, it cannot be like this, right? So this is the carrier wave, amplitude modulated by a audio wave. Audio wave is having two. This is AM1. This is, what you call 2 pi. 3 into 500 will be the FM1. This is AM2. 5 into 500 will be the FM2. So this bracket should have not come here. This bracket could have, there's no meaning in putting this square bracket over here like this. It is a wrong way of representing. It cannot be like this. Okay. So estimate the total power in the side band. So it's a multi-tone kind of amplitude modulated wave with the carrier frequency being 500 into 10 to the power of 3 and AC is equal to 4. Okay, 500 into 500 kilohertz is the carrier frequency, whereas here it will be 1500 will be the 1500 will be the so to say FM1, FM2 will be 2500. So all that you can just try to find out. Then you have the coherent detection of the DSB SC modulated wave. We have gone through the coherent detection. Uh, that can be done very easily. Okay, so this is just FM1 and FM2. Please solve this. Now let us go to the next question paper. Have we finished with that question paper? No, I think we have the second question also. Discuss the concept of frequency translation process with the help of block diagram spectrum. Again, frequency translation is already explained. Then explain the system of quadrature carrier multiplexing. This is also done. Compare the parameters of DSB-SC with VSB modulation. So DSB-SC will have both the side bands. VSB will have only one of the side bands, and other side band is only partial. Then what are the applications of DSB-SC? What are the applications of VSB? Then all the properties we can try to explain with respect to the DSB-SC and the VSB. Let us go to the next paper. Define amplitude modulation, explain the generation of AM wave using switching modulator. You need to explain the switching modulator. Coherent detection, same thing again. Costas receiver for demodulation. Obtain expression for spectrum of a single tone AM signal. Show that the total power in the sideband is 1/3 of the total power in the modulated wave with 100% modulation. So PLSB is equal to, we know that it is, so to say, the value total power will be naturally PC into 1 plus mu squared by 2. Only in a in the side bands it will be mu squared by 2 into PC. So mu squared by 2 into PC divided by 1 plus mu squared by 2 into PC is what we will get. PC will cancel. When mu is 100%, that is 1, we will get half divided by 1 plus half, that is equal to 1 by 3, and that will just give us the value 1/3. Then the second question, what are the modified forms of amplitude modulation? You need to write DSBSC, you need to write the SSB, then the VSB, all that briefly, very briefly, and then write a circuit diagram. And what are means, you just need to list AM, AM, then DSBSC, then SSB, SSB, and then the value of VSB, then VSB. All this you need to list. Then you have the ring modulator here, that has to be explained. Right, with the help of an amplitude response of VSB filter, explain the VSB modulation and demodulation process. So both the generation as well as the reception component of VSB has to be explained, right? That is there in the notes. Okay, generation is nothing but the modulation, and demodulation is just the reception. Right, you have the generation, which is modulation, and then the demodulation, which is there over here, which is nothing but the reception. Then consider a square wave detector using a nonlinear device whose output is defined by V2t is equal to A1 V1t plus A2 V1t square, where A1 A2 are constant and V1t is equal to this. Evaluate the output V2t. So we need to just substitute over here the V1t and V1t squared will give us again cos squared 2 pi of Ct, that is equal to 1 plus cos 4 pi of Ct divided by 2, right? Then how the message signal can be recovered from V2t, you need to describe that by just putting through the low pass filter. You can remove this off, and what is left is only the value of the, which is proportional to the, you can just remove both the 2 pi FCT, as well as you can pass through the low pass filter by removing both the carrier frequencies, upper FC as well as 2FC, both you have to remove, and hence you can recover. That has been, I hope it has been solved by us. Now let us go to the, okay, I think we are finished with that. With this, we can just stop